Hi, everybody. So I know people are still joining and we'll give them a chance to do that, but we're 5 minutes in, so I do want to get started with things. Thank you all so much for joining us. Let me share my screen really quick. Let's see. All right, oh, I can't see your faces, so oh, I can see some of your faces. Can you give me a thumbs up if you can hear me, if you can see the screen? Great, cool, awesome. Well, thank you so much, everybody, for joining us for project presentations. We're really, really excited to see what you have been able to accomplish across Project Week. Before we start, I just want to give you a huge congratulations. You did it. You made it to the end of Project Week. I know that was a lot of work. We've been kind of monitoring the conversations on each of the Slack channels, and we know that you've made so much progress. So press Z, do a little dance, give yourself a pat on the back. You definitely deserve it. That was an intense week and you made it to the end of it. And not only that, you got through all 12 weeks of this course and the many data exercises that we assigned. We know that that was a lot of work because we wrote those data exercises and they were a lot, we know. And also you submitted all these amazing project ideas and then worked on them this week, like integrating all the reproducible science techniques and data analysis techniques that we told you about over the course of the lecture part of the course. And we're just really, really excited to see what you were able to achieve and proud of you for kind of putting yourself out there and learning these new things and going into the real science world and you know, doing stuff with them on these really amazing projects. So today, like I said, is the team project presentations to tell us what you were able to achieve over the week. Before we jump into those, though, I want to just talk about what comes next, right? After today, everything's done, right? Party over. No, just kidding. So you're still gonna have access to the Slack after today, which is great because I know that you guys have been conversing with your teams quite a lot on that platform. So that's gonna stay here. Keep talking with your groups if you wanna keep working on these projects. The Slack will be a space for that. And you can also use GatherTown if you want to continue collaborating with your teams through a video platform like this. This will stay up here for the indefinite future. And then also we're going to keep the Jupyter Hub open until the end of March. So that means that you can use the hub to finish any of the analyses that you've been working on that maybe you didn't have quite the chance to finish before today. And if you need to move anything off of the hub that you have created over this past week, then go for it. We can post in the Slack some helpful commands that will show you a bit more about how to do that. We do ask that you definitely not remove raw data or all the pre-processed stuff from fMRI prep or QSI prep that exists kind of elsewhere to take off the hub and put onto your personal machines. That's just going to be a lot of really heavy data transfer, and it might slow things down and eat up some of the cloud credits that we purchased for this. But all the other stuff that you've been working on, absolutely. You can feel free to take that off of the hub with the caveat, obviously, that according to your docs, you need to store that data on a secured password protected computer. And then also after today, we really hope that you continue to make your code openly available on GitHub and that you continue to use reproducible practices in your data analyses. And we also really hope that you and your teams are able to turn the work that you did this week into reproducible publications. As we mentioned before, us, the ABCD-ReproNim team, don't expect to be co-authors on any of the papers that come out of this. The only potential exception for that is if a TA from the course kind of took off their TA hat and joined your team as a contributing team member, that would be the exception. But we do ask that if you found this course helpful and if you found this project week helpful, please do acknowledge the grant that made ABCD-ReproNim possible in the acknowledgement sections of whatever papers come out from this. And one other thing that's not a bullet point on this slide, but I am going to send out a survey in just a little bit, maybe a day or two, asking you how project week went and how the course went for you guys. And I really hope that you're able to fill out that survey. That will give us some really valuable feedback for what are some of the things that worked great, what are some of the things that we need to work on for the next time we offer this course. So look out for that in your email and please respond when you get it. And then last thing I just want to announce here is that immediately after today's project presentations, we're going to have one last social hour. It's going to be here in the GatherTown, but it's going to be in the game room, which is room 300, which is all the way down on the bottom of your screen. There's some cool games there. I think there's Tetris and Pong. And we just want to have one last social hour before we say goodbye to this course cohort. All right, so with that, we are welcoming our team project presenters up to the stage. So the order for things is on both the project outline and also in the details for the Google Calendar event for this team project presenters event here. So I'll call up people in the order that is outlined there, and either have your representative that you guys have elected to come up to the stage, or all of you guys are welcome up to the stage. If you stand on one of the podiums, we'll be able to see your faces, and you'll be able to share your screen with everybody. And we hope that you give us a note about whether or not you're planning to keep working with your project and your team after today. So with that, let me stop presenting this and then go back over here and invite the first person up here, which is proximal family risks as predictors of functional connectivity between the amygdala and frontal parietal network. This is GitHub issue number 19. Hi, Ali. Hi, Megan. Welcome.
There. If I share my screen, will she be able to if we're both presenting, I can just be the one sharing it, right?
You know, that is a great question. I think, yeah, so if you share your screen, you'll be presenting, but if Megan unmutes herself, I believe we will still be able to.
Okay, and I can just click through it. Okay.
Yeah.
Cool. Alrighty, so as you may have noticed, our title got a bit of a facelift. We used to be development of amygdala functional connectivity. My name is Ali, and Megan is my teammate on this project. So we can get started here. So again, just some background information. We know that amygdala and functional connectivity with the prefrontal cortex is a primary neural substrate of emotion processing and regulation that undergoes change throughout development. Specifically, we see a switch from positive to negative functional connectivity in these regions around 10 years of age. And children who experienced early maternal deprivation kind of had early emergence of this mature or negative connectivity profile. And so essentially overall, we know that amygdala functional connectivity is variable during childhood and sensitive to social relationships early in life. And so that led Meg and I to ask, can we leverage the ABCD study to explore amygdala functional connectivity and familial measures of social adversity? And so our hypotheses were that proximal family risk, so specifically risk close to the participants, and protective factors contribute to brain development and specifically shape the development of the network connections between the frontoparietal network and the amygdala. And so our expected outcomes were that there would be associations among these proximal family risk and protective factors, such as the parental mental health, trauma exposure, family conflict, and caregiver acceptance. These factors would be associated with functional connectivity between the frontoparietal network and the amygdala. And together, these factors would provide a good fit within a structural equation modeling predictive framework. And so I will pass it on to Megan to talk a little bit about that model.
Yes. So we really considered early life adversity, but we wanted to consider those factors that were most proximal to child development, specifically the parent-child relationship and the direct environment that the child is growing up in. And so in our hypothesized model, we look at parental symptoms of mental health as measured by the adult symptom report, the adult version of the CBCL for the parent. We also utilized the family history questions about mother and father, and if there were any substance abuse or drug abuse difficulties, depression, anxiety, severe mental illness such as mania or suicide attempts. We also were interested in child trauma exposure, and we used the KSADS, presence or absence of different trauma exposures, including community violence, interpersonal violence, sexual victimization. And then we looked at family conflict. Family conflict was measured in 2 ways. One with the child report, and that loaded onto a scale, and then the parent report of family conflict within the home. And we also wanted to consider resilience factors. So how accepting does the child feel that the caregiver is, specifically their primary caregiver, but also another caregiver. And we wanted to look at the predictive nature of these factors together and how they can predict resting state functional connectivity between the frontal parietal network and the amygdala, both left and right. So while we're presenting one model, actually the models were tested separately for the left amygdala and the right amygdala. So you can switch, okay. So in addressing the expected experimental outcomes, we wanted to first look at the associations among the different proximal risk factors within the data. And surprisingly, the associations between acceptance and family conflict were lower than what we would have expected. And additionally, the association between trauma exposure and family conflict was also very small. And there was no association between the resting state functional connectivity in the left amygdala or in the right amygdala with any of the proximal risk factor or resilience variables that we looked at. Also, so as I alluded to when I discussed the hypothesized model, that family conflict was measured in both parent and child, and the child report of family conflict in the home did approach significance for resting state functional connectivity of the right amygdala. However, it wasn't significant. So I believe it was a very small association at p equals 0.08. But that does indicate that there is a difference between parent report and child report of family conflict in the home, because the parent report of family conflict in the home was not approaching significance at all. In fact, it was like p of 0.5. So just not, there's a difference. And because of that, we modeled the structural equation model differently than hypothesized. So of our hypothesized model, so typically if correlations are very small, I would not run a structural equation model because you're not gonna find anything. However, because we hypothesized that, I did wanna test the full model. And so what we found is that all of the latent variables, the measurement models for those latent variables, were actually adequate to good fits of the data. So that suggests that there's some reliability in the measurement construct itself. However, it did not predict the resting state functional connectivity between the frontal parietal network and the amygdala, or in both the left, or in either the left or the right side, the left or the right amygdala. All of the analyses were conducted in Python. And so there is a package called SemoPy that utilizes the structural equation modeling framework. And I compared those results with a proprietary software just to make sure. It was my first time using SemoPy, so I wanted to sort of compare, and M+ and SemoPy really gave pretty equivalent measures and models, and so I feel confident in the results. However, they weren't what we expected. So to us, it was really interesting that even like the well-established associations from the literature and the psychology literature about parental mental health, family relationships, parent-child relationships were very small in this particular study. And so it was interesting to sort of think about when you have a population. So our final N was 5,363 children. So we excluded based on different diagnoses like schizophrenia or head injury. And we excluded siblings. And yes, so we did some exclusions. We had over 5,000 children. So when we think about sort of the psychology studies with an N of 200, and they're finding these, medium to large effect sizes for these sort of proximal risk variables, but the effect sizes we found were very, very small. And I think that really sort of points to the Merrick et al. 2020 paper towards reproducible brain-wide association studies. I really recommend everybody read it. It's sort of sobering, but it's also the reason why ABCD exists. And so, yeah, and I do think that sort of the measurement of the constructs we were interested in were reliable for the content area. So I think that that's a good thing, although we didn't find what we expected. So we also felt like the analysis wasn't the only thing that was important. And so we really successfully collaborated using Python code on GitHub. We had some very interesting experiences with merging and pulling and pushing, and so really good experience that we wouldn't have had we not been collaborating together. We successfully navigated how to utilize containers. All of our analyses were used using an open science data language, which was really new for me. I'm used to M+, SPSS, and so doing everything in Python where people will be able to reproduce that easily was really exciting. And we were able to collaborate with other ABCD-ReproNim students, which was also super exciting.
Yeah, and just as a quick note, again, we think, our like reasoning and our model and our code are pretty sound. So we are sort of just interested in conducting our own functional connectivity analysis in the future as sort of beyond the scope of this week project. And so, yeah, just in general, we are hoping to continue working together. And we just wanted to thank, everyone involved in this course, the other students, the instructors, the TAs, and everyone who kind of helped to make it happen. So thank you.
Thank you so much, guys. I think you guys have made awesome progress. I think that there's a lot of ways in which you can kind of keep moving this project forward if that's something that you want to do. And also just a note, I think it's really important to publish null results. like just in general. So great job, guys. If anybody, I forgot to announce this, if anybody has any questions or comments for the groups after the presentations, there are 2 podiums on either side of the stage. So come up and ask those questions if you want. With that though, I'm gonna move on to the next group just because I don't wanna run out of time here, which is a pre-adolescent imaging-based brain parcellation. So great. Wait, hold on 1 second.
Hi, you can see my screen?
Yes, we can see your screen. Go for it.
Awesome. So hi everyone, my name is Jessica. My team had 6 members, so Julio, Grace, Dustin, Helen, Adam, and me. And the goal of our project was to create a parcellation using pre-adolescent subjects from the ABC dataset. Just a very short background introduction here. So, we know that the brain is organized into multiple functional networks, and our analysis was heavily inspired by the results published by Yale et al. In 2011, where they used rest and state functional MRI data and identified 7 and 17 networks in a group of healthy adult subjects. And not only have these networks have been widely used in cognitive neuroscience, but multiple parcellation schemes have also been published in the last decade. But all of these parcellations have in common that they divide the brain into a number of regions based into homogeneous characteristics. But as I mentioned before, these parcellation schemes are primarily from healthy subjects' brain scans, and it's common to use the adult parcellation regardless of the clinic and demographic characteristics of the studied population. So with this project, we wanted to create a parcellation using the pre-adolescence data and compare the results to those obtained with the adult data. So before I go into detail of our results that we obtained during this week, I just want to briefly describe the methods that we used. So the code for the original paper is publicly available on GitHub, and we adapted it to run on our environment. What are the inputs that we used? We had rest and state filtered time series from the DCCAN derivatives. We smoothed the data and transformed our data to the FS average 5 surface space. Once we had the subjects in the correct space, we calculated the Pearson correlation between 1,175 regions, and the localization of these regions are shown on the bottom of the slide. So those from here, I don't know if you can see my mouse, but I'm scrolling over it. And as a last step, we projected the correlations into a hypersphere and performed a variant of the K-means clustering. Now, what we covered, now that we covered the method, let's just go into what we did this week. Our project can be divided into 2 parts. On the first part, we selected subjects from the ABC data, and on the second part, we adapted the Yale code. So let's just first focus into the first part. So we performed a literature review for different motion thresholds. We used the recommended threshold for the ABC-based manual of quality control. We used the registration, retained frames, and field of view, and we also used a main frame-wise displacement cutoff of 0.1. Then we selected typically developing kids. In particular, we used the KSDAS diagnosis and the child behavior checklist. And lastly, we needed to transform the data into the FS average 5, which was the format which the Yale code expected as an input. And on the second part of the project, we worked into adapting and running the Yale code. And in the spirit of reproducibility, we created a singularity container with Octave and FreeSurfer. We ran the Yale et al. Analysis with 2 sample subjects to see how we could get our analysis to run with our new pipeline. And oh yeah, before I forget, all our analysis, we focused into the 17 network parcellation only. And as a second experiment, we ran our pipeline into a few selected subjects that satisfied our criteria defined in the first part of the analysis. That is how we defined the normally developing kids. And we had a mean frame displacement of 0.1 from the ABC data. So now let's look at the results. So as I mentioned, for the first analysis, we were running the example subject from the Yale code and our pipeline, and we wanted to see how similar were the different results. So on the top row of the image, we have the parcellation that was generated by the Yale code using MATLAB. And on the bottom 2 rows, we have the results generated by our pipeline using Octave. And as you can see, although the inputs are the same, just by having two different softwares and possibly a different operating system, we obtained different results. From our first analysis, we learned that our pipeline works. We did not see a perfect overlap between the softwares, but we were not too disencouraged. We ran our analysis again using the ABC dataset that we have selected. So we had 82 normally developing kids. And this is our incredible parcellation for the pre-adolescence group that we have on the left. And on the right, as a reference, we have the parcellation that Yu et al. Reported in his 2011 paper. And this parcellation was obtained using the adult subjects. And we don't have a perfect match between the colors, but again, if you can see my mouse here, the second brain on the bottom row and the one on the bottom row of the Yale curve have a very nice overlap. The colors are different, but if you look, for example, regions are very similar. The way they are mapped is very similar. So just to summarize, we were able to reach our goals for this week. We generated the adult parcellation on, we generated the pre-adolescent parcellation on a small subject of the data. But obviously we are not done here. There's still a lot of work to do. And we have agreed that we will continue to work on the project after today. And those are a few of the points that we still need to address. So we need to compare the parcellation between the adults and the children. We need to find a tool to compare the different parcellations. So far, we have mainly visually analyzed the different parcellations, but we might have a closer look into tools such as Brain Smash and Spin to get like a more quantitative analysis. And similar to the work done by Yale, we will split the sample into discovery, where we'll find a parcellation and a replication group to see how well the parcellation overlaps between the different set of subjects. We have selected the strict motion correction for our first analysis, but we would like to see how much motion changes our parcellation. So we aim to calculate our parcellation using different motion thresholds, and we need to compare neurotypical with at-risk groups and determine the best cutoffs for the best groups. Lastly, we need to investigate why MATLAB and Octave are yielding different results. But our code is all available on GitHub, and you can go and check it out, play with it. It's also in a Singularity container, so it should work. And again, thanks to the organizers and the DAs. We had so much fun during the project week, and stay tuned for our final results.
Awesome. Thank you so much, Jessica. You guys have made excellent progress this week, and I love your future directions too. Okay, so I want to make sure we keep going with things. Again, if you have any questions, come up to the two podiums on the side. But I got a little confused just a little while ago with the order presentation. Some people did email us asking to go towards the beginning. So we're going to actually move one of the other teams that I had listed below up, and we're going to go with using multivariate statistical techniques to investigate the role of brain volume and neurite density on psychopathology. Come on up, guys. Thanks so much. Sorry, I forgot that you were going second.
Oh, no, that's fine. I'm going to share my screen.
It's totally fine. It's a lot of fun running around with these avatars. So we actually did have the upper where like we ran onto the stage and then we were like, oh my God, it's not our turn. And then we had to run back. So, you know, even in Gathertown, you can recreate awkwardness in real life.
Totally. We can see your screen. What we want to talk about is share our progress this week, but really tell you about all the fun we were having this week trying to figure different things out. So Claire Campbell, Rachel Custer, and I were part of this group. And so just giving a little bit of context, actually, before I forget, one really cool thing about this is that we can definitely work on all of this project in the future, because in just a few weeks, we will all be at USC. And so we can definitely and for sure continue to do this work and continue this. So keep an eye on us. So just a little bit of a reminder of what our project was.
project was essentially taking into account the fact that there are a number of brain measures that are available just broadly, right? We can always think about either structural measures or different sort of like diffusion measures like DTI and RSI. And so given that there's been a lot of research to relate these different brain measures to psychopathology measures, in particular CBCL scores, what we want to do is use a multivariate analysis, statistical analysis technique to really see if we have a model where we're really sort of putting in all of these brain measures, what can we find out about the different ways in which they all sort of contribute within a same model, all at the same time for these different CBCL scores as well. So the idea was to see if we throw these two sets of variables, brain measures and CBCL scores, can we extract some patterns, some reliable patterns from these that we can then use to follow up for in later studies, and also investigate sort of the more fine-grained contributions of each of those brain measures and how they relate to these different domains. So our big old project goals, number one was to assess the links between CBCL domain scores associated with psychopathology and different MRI measures. And so we'll go into a little bit more detail a little bit later as to which ones those were. But the ones that we were focusing on were RSI measures, DTI measures, and volume morphometry measures available in ABCD. I should also mention that although there's been many results of psychopathology, well, some results in ABCD looking at psychopathology and DTI in volume, we were also really interested in sort of exploring how does many of these RSI measures and how do they relate to psychopathology. And of course, because it's ABCD and ReproNim, another one of the project goals was to uphold FAIR principles and utilize best practices for reproducible analyses. So as we go along the way, we'll be able to talk about sort of how our workflow had these different principles and elements contained within that. So just a little reminder, because visuals are always useful and I love flowcharts. And so just a little bit about how the statistical analysis was sort of set up. So as I was mentioning before, we're trying to compare two broadly large sets of variables. And so over on the right side of this design plan, you can see that we were comparing the CBCL syndrome scores. And on the left-hand side, what we essentially did was we had 6 blocks corresponding to the 6 brain measures that we were going to use. So this was volume, FA and MD and the DTI measures, and then restricted, anisotropic and isotropic diffusion, and also total hindered diffusion in RSI. And what we did is, so we have 6 blocks here, and what we did is that we took ROIs to basically cover the entire brain. And so we did bring together ROIs from different types of data. So we used the APARC cortical ROIs for gray matter. And then we also used the Atlas tracks segmented white matter tracks as our ROIs for white matter. And then the ASEG segmentations to represent the subcortical ROIs in our model. And so later when I talk about these latent variables, it is sort of relating embedded within these blocks in these ROIs, brain measures to CBCL syndrome scores. And over on the left-hand side, why I went from right to left, I don't know. But this essentially followed the flow of what we were doing during this week. And so we'll step through that next. So I hand it off to Claire.
Okay, so our first thing that we needed to do was we needed to subset all the data, because you guys know that there are thousands of variables. And we decided to use the pre-tabulated data because we wanted to more work on the reproducibility and also wanted to use this PLS score. I am sorry about that car. And so we have the CBCL syndrome scores for 8 of the outcomes. We use the syndrome scores and not the total or the the other score, the other, what would you say? What would you call them? What would we call them? The internalizing and externalizing, or the total syndrome scores. We used each syndrome score specifically. And then we had the brain metrics for the whole brain that Carlos just went over. We had the RSI measures, that were 3 of them. We had the MRI, the DTI measures, so the FA and MD. And then we also had the volume. And then we also subsetted for demographic variables that we used in our analysis. And then we also subsetted for demographic variables that were in the collection, the matched collection by Damien Fair's group, where they had the matched subjects. And we also pulled those, so eventually later we can check that our subset of group 1 at least statistically matches their group 1. And then, oh yeah, Rachel can talk about how we pre-registered our project.
Yeah, so we pre-registered just to uphold those FAIR principles, also just kind of make a design plan. So pre-registering, in case other groups may not have done this, it's pretty straightforward. It walks you through each individual category, and essentially you would just put in, you know, what is your hypothesis, what is the study type, how many subjects are you using, describe the statistical analysis you're doing, key values you're using, etc. So this is ours. If you'd like to search it up, it is public. So you can go to the registrations on OSF and search this title and kind of view our full study plan and pre-registration there.
So then the next thing we had to do was clean the data. So I utilized the code that we were given in one of the exercises to condense all of the text files into one data frame. And we also needed a complete data set for our analysis. So we removed any subjects who had missing data. And then we also cleaned for QC variables for MRI analysis. So since you're using the pre-tabulated data, they had already provided certain metrics for being able to clean the data. So if there was high motion in the DTI, then we removed those subjects. We made sure to use the cleaning variables that we talked about for the 3.0 release. And then if they had any incidental findings. And then we decided to then also subset into each group 1 and group 2 based on the matched data sets. And that gave us a little over 3,000 subjects in each group. So not too bad. And then, so then I also decided to pull I ran all of this in Python, and this is my first time really using Python. I usually mostly do things in R. So I created some little pie charts based on our main demographic variables. This is just in group 1. And then we had some distributions of our race, ethnicity, and our parent education. And I also created a correlation matrix of all of the CBCL outputs. I just was kind of playing around with it, but they're not as clean as I would like them, but we've worked on them. And then one of the big things I focused on this week that I was sharing with my team was doing this in a containerized environment, and then I created a Docker image based on the Python environment and had requirements for the pip3 installations. And so I actually containerized the whole script to clean the data and pushed it to Docker's website so that it does work. And then the GitHub, I also pushed the original data, the original script cleaning analysis. And so it's not completely done because there are a few dependencies that aren't within it, but we are getting closer to it being completely reproducible.
All right, so I guess I should mention that for this portion is kind of where we went off the rails of the reproducibility choo-choo train. And so although the intention was to run these analyses in Python or anything else, I ended up running them in MATLAB. So just a little bit of a reminder so I can show you that we did get some results, although very sort of preliminary results. When running partial least squares analysis in trying to compare these two sets of variables, we can extract these latent variables that show the relationship between these two variables and also all the variables and components within them. And so ran this analysis to extract latent variables, and we also ran a permutation test and bootstrapping so that we can also evaluate standard errors for each of the loadings and also see which brain areas also contributed strongly to this latent variable. So next slide, please. Okay, so just one thing, so we ran these models across both groups, as Claire mentioned before. And so for both of these groups, even though you can extract many latent variables, in fact, as many as the number of variables that you have on either side, there were 2 latent variables for each of the models that were statistically significant once running these permutation tests. And so just to giving you a taste of what is happening. This is sort of the example of what the CBCL loadings look like in latent variable 1 in just one of the groups. So I wouldn't quote us on this, but essentially you can sort of see that for this first latent variable, the different syndrome scores, the different syndrome CBCL scores contribute in different way to this maximal relationship between the two sets. So here you can see that aggressive, for example, the aggressive subscale is contributing to this relationship in a different way that many of the other ones are.
Just jumping in really quick here because I don't want to run out of time for the rest of the groups. 2-minute warning, just if you can finish up in 2 minutes.
Oh, cool. Yeah, for sure. So if we go into the next slide, here are a bunch of brain ROIs and from the different regions that basically reliably contributed to this latent variable. So there's a lot of follow-ups that we need to do just to see what the specific relationships were in what direction, but at least we're able to identify some regions. And these are, this is collapsed from the whole set, which is like 120 ROIs. So.
Okay, so a lot of what I focused on this week was learning to visualize the diffusion data using DSI Studio, and the goal was to also learn Atlas Tract. So for DSI Studio, you essentially load in a diffusion weighted image, then you reconstruct that image, it creates this SRC file, and then you're able to use fiber tracking to view the fibers for each individual bundle. So here's kind of just an example of what it would look like in the process. So, when you load in the diffusion image, it asks you if the brain mask is covering the whole brain, and then it outputs a fiber tracking map. So just kind of to really quickly visualize some of the tracks that we did see more significant results in, you can see here we had the right and left usinate facets, the right and left inferior frontal occipital fasciculus, the right and left superior cortical striate, and the right and left superior longitudinal fasciculus. And the other ones in the box, as Carlos had mentioned before, these are just other tracks we had seen significance in that I didn't get a chance to visualize. So yeah, this is pretty much how our project went, and we have some next steps as far as continuing it. I'd like to learn to use Atlas Tract. I kind of was running into errors with the MATLAB code. And another thing just to consider is like this idea of reproducibility for visualization, since diffusion reconstruction usually involves like ROIs, it would be really nice to use Atlas Tract as it doesn't involve that, it's using an atlas of diffusion bundles.
So I am gonna just jump in here because I have to cut you guys off. I'm sorry, we got a little bit behind at the beginning. But you guys have done such great work, and we're chatting in the background here about how fun it must have been to work with your team. So thank you so much for your presentation here. We're gonna call our next group up here, and I'm sorry we're running a little bit late. Association between structural and connectivity characteristics in the language networks and the statistical learning networks in children's learning abilities. Again, sorry guys that we got a little bit messed up with the presentation order of things. Hi, Catherine. I see Bob coming up here too.
Yes, so what's going to happen is we ended up splitting our presentation a little bit, so I'm going to share my screen, and then once I'm through all the stuff that Marie and I did, Bob will go over some stuff with Deep that we did to expand what we were studying.
Awesome. And if you guys could be, I don't want to run into a lot of other people's talk, so we're aiming for 10 minutes here.
I can talk quickly, yes.
Thanks, Catherine.
So our group, as you have probably guessed by now, is studying the relationship between statistical learning and language skills in children from a brain connectivity perspective, specifically using the DTI results in children and the NIH Picture Vocabulary Toolbox and the Picture Vocabulary Tests age corrected from the NIH Toolbox as a proxy for language skills. So what Marie did is she took some ROIs from statistical learning in our lab and looked at them first initially with adults to see what some of the tracks we might expect to come up that were specifically implicated in language, such as like the left articulate fasciculus and its right counterpart, and similarly for inferior frontal occipital fasciculus, longitudinal fasciculus, unicate fasciculus, so we knew to look at those. Then we went into the pipeline for the trial data. So first we downloaded the relevant data from the process MRI package, and also the demographic and language core from that package. We used the standardized instructions from ABC to do that, along with Python scripts that I wrote to process it down to just what we needed. After that, most of what we did was running things in DSI Studios. So we'd first get them as open source images, then reconstruct the SRC files and connect geometry database for our low scorers and our high scorers in the language task. And we're specifically looking at FA in regards to this for DTI. And then after that, we ran 2 separate group connectivity analyses in the DSI Studio, one for low scorers and one for high scorers. Covariates of age, text, and the NIH vocabulary age corrected score. The last one being our study variable. We loaded our statistical learning ROIs in here so we could get tracks that specifically passed through them in our analysis. And we checked the normalized QA box because that controls in the program for differences between scanners and sites. So then once we got those connectivity maps, it turns out it came up with a positive connectivity map and a negative connectivity map for each group. We would take the individuals in that group and overlay those maps. And for like example, the positive connectivity on subject 1, we get the FA for the networks implicated in that along the tracks. And same with the negative, etc. for all the individuals. Then we used further Python scripts I wrote to get the average FA for participant, and from there used tests to see if there is a significance for the high group versus low group in the positively correlated tracks or the negatively correlated tracks. So before I go into this, I want to clarify that our goal this week was mainly to get the pipeline established in regards to this and make sure that we could generally run through the whole thing. So we only had 10 participants in each group. Thus, these results are preliminary enough that you should ignore 90% of them completely because they are not reliable. But some quick things to note that I think will probably show up again in a larger data set is, 1, there is crossover in tracks between the high group tracks and the low group tracks. For the positive correlation, there's a crossover about 3 tracks. For the negative correlation, crossover about 4 of the tracks that get implicated. And we did see things that came up earlier in Marie's work. For example, one of these tracks for the positive correlation that was seen in both was the inferior longitudinal fasciculus on the right side. And then similarly, the negative one got part of that track correlated as well, along with the articulate fasciculus on the left side. So we are seeing some language areas and their counterparts implicated in our work thus far. Another quick thing to note is the high group has a much more positive correlation than negative correlation, in contrast to the low group, which has slightly less positive correlation than comparatively negative correlation if you look at the number of fibers that get implemented. So we did, using further Python code I wrote, compare the groups for positive FA within that group and negative FA within that group. Neither are significant, which is unsurprising with the size of our data set, even if it's starting to approach significant with the negative FA group. So going forward, there are several things we want to do in regards to this pipeline. First is to flesh it out. We skipped a lot of quality checks on our data with the goal of making sure we could run through the full thing. So we would be introducing those and determining how to make sure that those are reproducible and well done. And also asking if there's any additional exploratory analysis we want to do. We also want to interrogate our design choices. For instance, in the DSI, we were just using the standard atlas for DSI. Is there a better atlas to use when looking at this trial data? And also analyze all our decisions within programs like that of defaults. Do we need to change them? Another goal is increasing reproducibility. I was not able to containerize DSI, unfortunately, on my computer. There were issues with that code. So going forward, I'm going to be working to resolve those issues so that we can do containerization and version control of DSI, as that is known for with updates changing the output. I'm specifically going to try to use DataLab because that's also good for handling large amounts of data to do this. And also now that we've established that there's a functional pipeline and we know sort of what we're doing, we're going to start on our registration on OSF. This isn't quite a registration to the full extent that those normally are because we have run through things, but we have no actual results for this pipeline with our small data set, so we're not too worried about that. We're also going to increase the automation of everything to limit human error and make sure there's less need for oversight when running things. And in addition to all this, Bob did some work on the larger data set since this was so small using Deep. So he's now going to present on what he did there and also discuss a bit about the variables we use to select our children on a very small data set.
Well, I can't seem to get on the stage. Can anybody see my
Actually,
slide?
we can see you. We can't see your slides. So if you go down to the bottom and click the kind of computer screen icon thing, then that will allow you to share your slides.
I did. It says to share screen down here.
Yeah, it says share screen.
I'm clicking on that. It's not working. Well, maybe I can't do that. Well.
Are your slides anywhere online that you could send to Catherine, and maybe Catherine could walk through them?
How about share here? Does that share anything? Oh, well.
Oh, we can't see them.
Oh, well.
Shoot, I wanted to see what you were able to do with Deep. If you perhaps, I don't know, just a suggestion, you could email them to Catherine and she could share them really quickly.
Okay.
That would work. Apologies, we didn't think about coordinating it as well as we probably should.
It's okay. You know, I love GatherTown for its many features, but it can be a little bit hard to, figure out.
GatherTown or Python?
Do you think we could do this within 2 minutes, because that's how much time we have left for your presentation?
Yeah, let me see. If not, she did a very good job of doing all this. So.
Well, I must say it does seem like you guys have made a lot of really great groundwork for moving things on to the next stage.
Yeah, it's not reproducible yet, but we at least have the groundwork to make it so when we expand it to a larger data set. So that's something I'm excited about.
Yeah, totally.
Okay. All right.
Perhaps we should.
We could go on.
Yeah, perhaps we should go on to the next group, and if you guys figure it out, then we can invite you up for the last 2 minutes of your talk. Does that work?
Okay.
Okay, cool. Sorry for the technical difficulties there that we experienced, everyone. All right, so we're gonna invite our next group up here, which is childhood unpredictability and reward processing. And Bob, if you could move off of the podium. All you have to do is click on the screen and then walk off.
I'm out of GatherTown now.
No, it's cool.
Okay. I can do that. Yay.
All right, welcome, childhood unpredictability and reward processing team.
Hi.
Hi.
I'm just trying to share my screen. Okay, I can just share my entire screen. So now can you see my slides?
Yes, we can.
Okay, great. So our group looked at childhood unpredictability and reward processing with Cassandra, Mingyang, Clara, and me. So a little bit background, altered reward processing and subsequent maladaptive decision-making is a potential mediator between early life adversity and later risks. And increasing evidence has suggested that it's not only the quality of early environment that matters, but its pattern also matters. For example, inconsistent rewards and punishments may change a children's reward expectations and hence lead to maladaptive decisions. But given the increasing interest in childhood unpredictability, there are a lot of ambiguities in how to define and measure this construct. So our first goal in the study is to extract variables that might indicate unpredictability in the ABCD dataset and inspect its latent structures. So our step 1 in this project week is to select and compute variables indicating unpredictability in each wave of the data. And then we use a factor analysis to inspect the latent structures of unpredictability variables for each data wave. And then we derive composite scores for each factor in baseline. which we can then use to examine the relationship between childhood unpredictability and reward processing and the monitoring incentive delay task. And for the sake of time, we use the tabulated baseline data only. So I'm so glad to let you know that we almost finished all 3 steps, which is really great. And so for the first goal, which is extracting or selecting and computing unpredictability variables, here is a summary of the variables that we selected for each data wave. And just for the sake of time, I won't go into the details, but if you're interested, I can definitely email this to you afterwards. And now I'm going to passing it to Cassandra to talk about the factor analysis across data waves.
So we did an exploratory factor analysis using the factor analyzer package in Python. Before we went forward with it, we did test that the data was adequate for a factor analysis. And this was 2 measures with the Bartlett test, the Ferocity and the Kaiser-Meyer-Olkin task. So just briefly for people who aren't familiar with it, sorry. The Ferocity test checks that the variables are correlated to indicate that there may be a latent structure. If it's significant, that means the data is adequate to use. The KMO test just tests the proportion of common variance across all the variables included in the factor analysis. If it's greater than about 0.6, it is good to use. And you can see on the next slide that the correlation matrices across the different waves are very similar, and it does show that there are these strong correlations across the variables, which is really exciting that we are getting similar patterns across the wave. Then on the next slide, we have the Scree Plots that are used to kind of see how many factors we can extract from the data. And from baseline year 1 and year 2, it looks like the 5-factor model was the best option, because that's where we see where the plot is starting to elbow and even out. So on the next slide, we do have a list of the factors that we extracted. And these are just the general factor descriptions on the left-hand side. And under baseline year 1 and year 2 are the specific factors we extracted. So one of them was trauma or negative life events. And what's really interesting, as we saw from an earlier group, is that the youth-reported life events and the parent-reported life events actually came out as separate factors, suggesting that there's something unique to youth reporting their events versus parents reporting their events. The other factors that seem to emerge are parenting styles and family dynamics, so how accepting and warm your parenting styles are, parental mental health or psychopathology, SES factors, as well as neighborhood safety, so crime and safety factors for the neighborhood. And then Lillian will present the results.
Yeah, thanks, Cassandra. So now with those factors, we can examine our central question of childhood unpredictability and reward processing. So just to recap, so here are the 5 factors that we extracted and input into the model. First is traumatic events and parental monitoring and warmth, parent psychopathology and behavioral problems, SES, and neighborhood safety. So after some consideration, we think that the first factor, traumatic events, it in itself may just indicate harshness instead of unpredictability. So we're going to use it as a control variable. And for the other 4 factors, they each can be mapped onto an established questionnaire of unpredictability in childhood. So that questionnaire already has some good psychometric features, so we're glad to see this mapping. So for example, the second factor can map onto parent monitoring and involvement. The third factor can map onto parental predictability and parental environment, whereas the last 2 factors can map onto safety and security. So after seeing this, we are good to proceed. And here are the ROIs that we selected for in the MID task. Because of the time, we only examined the first 3 contrasts, which are reward anticipation, reward feedback, and loss anticipation. So here are the results for each of the ROI. We input all 5 factors, which means that we are controlling for all of them. And we also control for the random effects of sight. So after performing the false discovery rate correction, here are some significant findings coming out of the preliminary analysis. So first, for the factor 1, traumatic events, we see that for those children with more exposure to traumatic events, their brain activation in the left VMPFC is decreasing significantly during the reward feedback phase. Because the VMPFC can do a lot of things, so we're still in the process of figuring out what does it really mean. But our current speculation is that so this reduced VMPFC activation in reward feedback might suggest a blunted reward reactivity, which might be related to anhedonia symptoms or depression symptoms that we can see in children after experiencing traumatic events. And then the other 3 significant findings are all related to the neighborhood safety factor. So this is after controlling for the SES, so I think it's interesting. So we can see that children who are living in more dangerous neighborhoods, their brain activation in the right amygdala, as well as the left and right rostral middle frontal gyres, are increasing after, in the loss anticipation phase. So here are the conclusions. So in this preliminary finding, we can see that living in more dangerous neighborhoods is associated with increased brain activation in amygdala and dorsolateral prefrontal cortex in the loss anticipation phase specifically. And this is after controlling for other adversity measures such as SES and parenting environment. So we think that is very interesting because it's showing that youth who are living in more dangerous neighborhoods, they seem to be more vigilant to potential loss, and they are engaging in more cognitive control when facing potential loss. So what does it implicate for decision making, which is real life outcome that I am concerning about? So I think that because of this increasing vigilance of potential loss, these youth might have altered reward evaluations and also altered subsequent action selection. For example, they might explore less about their environment, like trying less unknown things because of the fear of loss. And this is actually going to having some detrimental effects of learning, especially in early childhood, when you need to explore a lot about your environment to learn about those probabilistic relationships. And we do have limitations in this study. So one of the major theoretical...
Jump in really quick. If you could go through this last slide pretty quickly, that would be awesome.
Oh yeah, sure. Yeah, definitely. The theoretical limitation is that it's hard to measure the variance, chance, or a change or frequency of harshness with just a one-time score. So it might be hard to disentangle harshness and unpredictability, but I think that the repeated measures will help. And will just leave it out. And I really want to take some time to thank all my amazing team members for such a smooth and happy collaboration. And also I want to thank all of you for creating such a wonderful learning community. I think the interaction here is invaluable. Thank you so much.
That's very nice of you to say. And I think your results are fascinating. I'm really glad you guys have been able to make so much progress with that.
Thank you.
Let's see. Okay, so we're gonna invite, we don't have time for questions for this one because we're running a little bit late. So I would ask the rest of the groups to try and keep it to 10 minutes. So we're gonna invite our next group up here, which is effects of race and socioeconomic status on mental health trajectories of adolescents and older children. Grace, is that you?
Yes.
Hi, thanks. Yeah. And Lillian, if you could, I think you're still at a podium. Now we can see your screen. Perfect.
Okay. This looks good. Okay.
Yeah.
So hi everyone. I'm presenting on, my name's Grace. I'm presenting on behalf of my team. And so we have changed our research question a little bit throughout the week. And so the title of our project is now Effect of Socioeconomic Status and the Mediating Effects of Brain Structure on Mental Health in Children from the ABCD study. So low socioeconomic status has been linked to elevated psychopathology in children and adolescents. And then there's also a relationship between decreased gray matter volume and general and specific psychopathology. And then there's also a link between low SES and low brain structure. So we wanted to investigate the relationship between brain structure, psychopathology, and socioeconomic status, specifically in the context of stress. So we were interested in whether brain structure would mediate the relationship between socioeconomic status and mental health in children, because children exposed to low SES are often more vulnerable to higher levels of stress, and which alters the hypothalamic pituitary adrenal, or HPA axis, and can impact brain structure. And to also narrow down into specifically this relationship with stress, we looked at whether higher family conflict would moderate the relationship between SES and psychopathology, as well as the mediating relationship of brain structure between SES and psychopathology. As higher family conflict has been associated with elevated psychopathology itself, as well as changes in brain structure. So our research questions were, does brain structure, specifically subcortical volume for this study, mediate the relationship between SES and psychopathology in children? And then secondly, does stress related to family conflict moderate the effects of SES on psychopathology or the mediating relationship of brain structure? We expected that reductions in brain structure during this important period of neural development would mediate the relationship between low SES and higher psychopathology. Further, we expected that stress related to family conflict, higher stress would strengthen the mediation effects of brain structure on psychopathology and the relationship between SES and psychopathology. So here are the kind of more specific measures we used to look at these different variables. So for socioeconomic status, we looked at household income, area deprivation index, as well as highest parental education. For mental health, we looked at the internalizing and externalizing T-scores from the child behavior checklist. For brain structure, we looked at total subcortical volume. And for family conflict, we used a family conflict subscale, which captured violence, anger, and general family cohesion. So these are kind of the specific goals that we had for ourselves over the course of the week. We met a number of them, but we also ended up kind of changing and thinking through our research question a few times. So we learned a lot with that. And we're also really happy we learned a lot about data lab and reproducibility, and we were able to implement those tools. We also learned a lot about multi-level and moderated mediation models. Shout out to Katie for helping us out with that. And today I'm going to show you some results for a preliminary model we have. And we've also established an action plan moving forward after this week to keep moving with this project. So a little bit more about our sample, not to go into too much detail, but we started with, of course, almost 12,000 children, as you all know really well.
And after removing kids related to quality control of the T1-weighted imaging and free-surfer data, as well as participants who were missing CBCL data, SES, or family conflict data, we had 9,225 participants. So for our actual mediation model, we used Python, specifically the PyProcess macro package, and we based it off of Hayes' theoretical mediation model. We covaried for age, sex, and site. And to capture more than one socioeconomic status variable, we used PCA and took the first principal component, which captures 68% of the variance when integrating these three different measures of SES. So we found that lower SES was associated with higher internalizing and externalizing symptoms, as we hypothesized. And we found that subcortical gray matter did significantly partially mediate the relationship between SES and externalizing symptoms. So what that means is that increased SES did predict higher subcortical volume, and then higher subcortical volume in turn predicted lower externalizing symptoms. This was only significant for externalizing and not internalizing symptoms, though. We found that family conflict did significantly moderate the direct relationship between SES and externalizing symptoms, but not the indirect mediating effect of brain structure. So to kind of summarize, brain structure did partially mediate the relationship between SES and externalizing symptoms, and family conflict moderated the direct relationship, but not the indirect mediating effect between SES and psychopathology. And perhaps this is because family conflict might not be a strong enough measure of stress to impact biological processes related to brain structure caused by altered HPA axis functioning. So here's a little bit more information about our open sciences practices. So we use Data Lab to track our data and analysis. We currently have a private GitHub repo that we'll make public. And we are working on containerizing our pipeline in NeuroDocker. So some future directions specifically related to our analysis. So we want to nest effects of site instead of just covariating for it. We also want to look into integrating SES as a latent factor into our model, and potentially integrating more than just our three SES variables at the moment. We're also interested in going back and integrating race as we kind of initially planned at the beginning, but making sure that we also incorporate important potential contributing measures and context to explain any potential differences that we might find between race groups. We're also interested in seeing how our model extends to other brain measures. So stress seems to more highly impact subcortical volumes, but then SES seems to have pretty strong connections to more cortical related measures. We also want to investigate other measures of family or environmental stress that might have stronger effects on brain structure, such as the KSAD's subscale of traumatic events. And finally, we can also look at psychopathology at baseline, which is what we looked at, but also longitudinally, which children have kind of persisting or worsening symptoms, and whether that is related or mediated by brain structure, the relationship with SES. So just want to end on thank you very much. Thank you to Katie for helping us, walking us through mediation models. And then Angie, thank you so much for kind of helping us develop our research question. To Dustin, and in general, the entire ABCD-ReproNim team. This course has been really fantastic, and this week has been a really great experience. So thank you so much.
Thank you so much, Grace. That's so good to hear. And I think the work that you guys have made is fascinating, and again, really good groundwork for moving it on for future directions too. All right, awesome. So let's see. If anyone has any questions, you can come up to the two side podiums and ask them to Grace. Grace, if you could stop sharing your screen for now. If we don't have any questions, which it looks like we don't, then I will move on to the next team, which is functional connectivity and emotional working memory and anxiety. Hi, Morgan. Hello. And just a reminder to try and keep it within 10 minutes, just so that we don't run over time.
You got it.
Thank you.
Good.
Yep, good. I'll hold up 2 minutes when it's a 2 minutes warning, okay?
Perfect. Cool. And I have a little timer going on my presenter view, so hopefully I can also keep track of it. All right, so as a reminder, we are Project Anxiety and Working Memory, and I am Morgan Glover. Collaborators Dakota, Klimovich, I actually have never heard her say it, so I hope I pronounced it right, Anna Howard, and Adefunke Dade Matthews. So I want to just give you a little overview of what's the big idea. So why did we do what we did? We were all interested in working memory, anxiety and stress, and emotional saliency, and their interactions, if there are any, which we do think there are. However, the relationship between working memory and everyday stress or anxiety is less known in non-clinical populations. This is seen in a Frontiers paper, which was published in 2019 with large populations in just a survey of adults. They found a trend in towards a negative association between working memory performance and anxiety, but not with stress. Also, a Journal of Neuroscience paper in 2020 analyzed the ABCD data to establish relationships with working memory and frontoparietal brain activity. This can aid in longitudinal changes in working memory and predict later academic outcomes, which is really good for everybody in the world. So really good thing to keep on going, which is also why we're interested in this study. Our main question is, does neural activation during the emotional working memory task, the EN-BAC, relate to reported measures of generalized anxiety? And so what we did is we started looking at emotional saliency via the emotional and neutral faces in the EN-BAC. First, we examined 24 ROIs, which were the cortical and subcortical related to anxiety. So I say 24, but I actually kind of mean 12 in both hemispheres. Just 24 total. All right, so progress, initial goals, and where we are. A little bit of a reminder, because we've done this a few times, and so you might remember a few bits of this. On Monday, we had hoped to finalize our hypothesis and analytic strategy, finished collecting data. That bit didn't happen until Wednesday. We had a little bit more cleaning up of the data to do, but we actually still got it done, so cool. On Tuesday, we wanted to work on the task-based fMRI analyses, but that also didn't happen on that day, but we also got it done. And then on Wednesday, we wanted to finish the task-based fMRI analyses. Also didn't happen on that day, but we still got it done. So all of the things kind of still happened, but were pushed back 2 days. However, we did not get to generate any figures, which you will see on the next slide of why that is the case. All of our goals, though, were met. We did analyze the behavioral data, we analyzed the fMRI data, the tabulated data specifically, and we did both of these things in R and in Python, so we could kind of translate everything. So preliminary findings, we've got some good news and some bad news. I'm going to start with the bad news. So, well, still, any news is news, right? There's no significant associations between the brain activity during the emotional versus neutral face contrast and anxiety. So we have hypotheses that this could be because there's good news that there are not a lot of anxious kids, right? That's pretty good. So in total, the N for our study was that there are 7,816 that did pass that QC measure. And since we were using the tabulated data, what you've heard a little bit earlier today, they passed those 3 criteria, which was passing the free surfer QC measures, having an accurate, or not an accurate, having an adequate performance on the NBAC task, and then also having minimal movement. So as long as they passed these things, they got included in our analyses. And then the kids that had a clinical risk of anxiety, out of those were 544, and this was measured with the CBCL, what we used for the CBCL was a reported score for anxiety. We only used the generalized anxiety or persistent worry measure. We didn't look at any questions about phobias or social phobias. So maybe that could also be something that we can investigate in the future. So not a lot of anxious kids, pretty cool. However, because there's not a lot of anxious kids, the measure of anxiety may not be very robust, which is maybe leading to the non-significance. So we just kind of need to work on buffing up the measure. And with that over 65 for clinical risk with the CBCL, and there's 544, over 70 is actually only 233 kids. So pretty low. Our fixed effects and our random effects for all of these were, as I explained, CBCL, interview age, sex, race, and ethnicity, and combined family income were fixed effects, and then random effects were the ABCD site and family. We used a linear mixed effects model to do all of these things, but plan to work on getting some generalized additive mixed models in the future. It just didn't work out this time. Future plans. We're working on containerizing a workspace, currently in progress, so cool. We're working on uploading the code to GitHub repository, also currently in progress, cool. These things were like on our soft to-do list for the week, not on our like, get these things done for sure. We knew we wanted to do them in order to abide by the FAIR principles. However, we wanted to make sure we also had something to present today. So it was a generous task that we wanted to complete. And we are work in progress, so good pin to stop on. We also want to consider running similar analyses with the working memory portions of the emotional NBAC. So to investigate the measure of anxiety with the 2 versus 0 back conditions and the relevant ROIs with that. We also want to, like I said, consider a more inclusive and robust measure of anxiety. So potentially a latent factor analysis with the CBCL and then include the KSADs as well. So maybe the kids have a different measure of what their own anxiety looks like. We didn't include this originally because we didn't really know how reliable it would be with 9 and 10-year-olds reporting their anxiety. And also when we first looked at the count, there were not many kids that were reporting their own anxiety, which also no anxious kids, cool. We are also considering performing cluster analyses on emotional saliency brain regions instead of looking at the anatomical maps. Because the anatomical maps are what is calculated for these tabulated data and not a functional analysis, we are considering the cluster analysis. So the ROIs are currently a broad region that explain the anatomy and not necessarily specified to the function. So examining a smaller area like a 1 or 2 voxel region as opposed to a wider area could lead to a better significance as well as looking at that anxiety measure. We also want to consider what this would look like as a manuscript. So are there enough findings? Did we do enough for our analyses, and does this contribute to a gap in the literature, or should we add more? And then also, of course, take what we've learned throughout the week and the whole course beyond and into our careers and further all of science.
Last goals.
Not least, I want to thank all the course organizers, instructors, teaching assistants, technical support, because yes, never forget that, and content writers, this cool group, and all of the students in this 20 to 21 cohort. And that is all.
Thank you so much, Morgan. Excellent presentation, excellent work this week. Now that I'm like literally here on a soapbox, I just wanted, broadcast to everyone. It's cool to publish null results. That's important. That's an important thing to do. So nice work. We hope that you keep working on this.
Great.
Cool. With that, let's see. I'm going to, I don't see, if you could stop sharing your screen. So, okay, there we go. I don't see anybody at the questions. So I'm going to move on to the next group. which is typologies of temperament, identifying adolescent temperament profiles that predict substance use risk factors. I see Lauren coming up here. And Arsh, awesome. Hi, you guys. Yes, I can. And I'll hold up 2 minutes for 2 minutes and 1 minute for 1 minute warning.
Okay, can you try talking again, JB?
Yeah, can you hear me okay? Oh, we have technical difficulties. We can see you though. So if you want to share your screen and we can hear you too. I can't see.
I'm gonna get started.
You're good though.
Or I can't hear you, I'm sorry. I don't know why this happens only to me. And it's only when I get on these little soapboxes. Okay, so I am Lauren. I am with the Typologies of Temperament group. And so I'm going to be presenting today some of the work and results that we've been working on this week. So the intention of this project was to identify temperamental dimensions and typologies within the ABCD cohort using latent profile analysis on the early adolescent temperament questionnaire. And further, we sought to examine whether these dimensions and typologies significantly predict neurocognitive risk factors for psychopathology. And we didn't look into substance use at this point, just because they are not using. So our first research question was, within the ABCD cohort, what are these study-specific temperamental dimensions and typologies? And do these differ by biological sex? So to achieve this goal, we downloaded data using Data Lab and created a project GitHub repository. We prepped the input data for the latent profile analysis by calculating missing data and scaling indicators. We calculated sample descriptives, which is here on the right-hand side. And then we were able to conduct the latent profile analysis. So our entire sample was about 6,600. And so you'll see within this pink box a breakdown by the latent profile analysis groups that we identified. You will notice that something to take into account when I go through the results today is that there are groups, there are profiles with a low amount of subjects in them, which is concerning, but we are working on rerunning the model with the appropriate parameters to make sure that everything is tied up and accurate. So for the latent profile analysis, we ran it in R. The indicators that we included in the model are from the EQ superscales. So it's effortful control, surgency, negative affectivity, and affiliativeness. And so the covariates that we took into consideration were age, sex, and sex is like when we run the LPA model with males and females in it, but obviously it's not included when we run the model separately for males and females. We have race and ethnicity, combined income, and then the nested variables of site and family. So one of the big challenges for this project was running the latent profile analysis in R. So many of the packages do not include the ability to have covariates controlled for appropriately. So we tried to run this like in a novel way, I would say, using residuals from linear mixed effects models. So a lot of what we've read for the LPAs, a lot of people use M+, but M+ is, you do have to pay for it. So we wanted to be as open as possible. So we tried to do this in R. And so for the LPA, we compared a model fit for including both males and females in one model, and then we ran models separately for males and then for females, because we do suspect that there would be biological sex differences in temperament. So the criteria that we took into consideration for the LPAs is entropy, AIC, BIC, and then the min and max profile sizes, which I alluded to a little bit earlier, that we are concerned about our minimum number there. But we are in the works of rerunning the model, so they are looking better. And then BLRT.
So we had identified that model fit criteria was improved for running separate latent profile analysis by biological sex. So that's what I'm going to present here.
We actually can't see your slide.
So for the latent profile analysis, at the top here, we can see the model fit criteria. So we had wanted AIC and BIC to be low. And then traditionally we would like entropy to be 0.8. But here it's 0.69, so that is a bit low. And then here's what I was talking about the lower number of subjects and profiles. Oh, it's not sharing. Is my screen not sharing?
Yeah, that's correct. Sorry, Lauren. I know you can't hear us, but we're not able to actually see your slide. So if okay, now we can. Great. Sorry about that.
Okay.
Oh, technical difficulties.
I'm so sorry.
Today.
I don't know why I have technical difficulties.
We're good now.
Thanks, Taylor. Oh my gosh. Well, at least there was really nothing on those slides. Okay. So let's see, where was I at? Okay, so for the females, we identified the 3 latent profile solution. And so here on the x-axis are the superscales from the EAT-Q, so effort for control, negative affectivity, surgency, and affiliation. So these are the loadings within each profile. So you can see that the first LPA profile, there's high effort for control, negative affect, surgency, and affiliation. And so you see like this lower affiliation value within the second profile. So that is interesting to see the differences, and we would like to associate these more with behaviors moving forward. And so we did similarly look at this for males. And so within the males, we had found that the 2-profile solution was the strongest. So again, looking AIC, BIC, and then here the entropy is above 0.8, which is great. But then again, our smaller profile, which is a little concerning. So we do see much of the differentiation here on this affiliation scale. Our second question was, do these typologies parallel prior work or offer a novel solution? And so this is to be determined. We still have some interpretation to do, but we will be on that soon. So our third question was that to see if these identified temperament profiles are predictive of neurocognitive risk factors for psychopathology. So we had focused on psychopathology here and then task behavior. So we'd used the raw data from the CBCL to calculate 5-dimensional factors. And so I'll explain that here in a moment. And then we also looked at behavioral performance on the NIH Toolbox flanker to get inhibitory control and attention, and then the pattern completion task, so processing speed. So then we examined these associations between the profiles and then these behavioral measures using linear mixed effects modeling in R. And so these 5 CBCL dimensions were identified from another paper that looked within the ABCD study and found a hierarchical structure of general psychopathology with these 5 specific factors. So these are what we're using moving forward. So internalizing, externalizing, detachment, somatoform, and neurodevelopment. And so these were validated with risk factors, cognitive functioning, and real world functioning, and they're largely consistent with prior factor analyses work and this high-top framework. So these are very preliminary, but we can see, so each graph here is one of the 5 CBCL dimensions. And so within each of them on the y-axis is the profile. So here's the third one, second one, and first one. And these are a reminder of the 3 profiles below. So these blue bars are the confidence intervals for the estimated marginal means. These red arrows comprise the comparison between the profiles. And then if a red arrow overlaps with another red arrow, that means that there is no significant difference between the groups. So here we can see that there's a significant difference in internalizing between our third profile and our first profile,
but not between the second and first one. So we can kind of see this similar relationship in the neurodevelopment. And I will hurry up. So those are CBCLs. And so here is the toolbox on NIH behavior. So we also see some differences in task behavior, which is really interesting. So not only on measures of psychopathology, but task performance. And then males were just internalizing and detachment here. And then I will let Arsh quickly explain some of our open science practices here.
We think you're muted, Arsh. There we go.
Yeah, as you can see, we used a bunch of tools, but towards the end, we were not able to use the Neuro Docker to containerize our workflow. But Lauren, could you move to the next slide?
And we have just 30 seconds left, so if you could go through this one quickly. Sorry about that, Arsh.
That's all right. You can, Lauren, you can go to the last slide. We basically just created the GitHub repo for the private repo. We have most of it there. We need to make it public. So maybe in the next couple of days, but yeah.
All right, so I am going to cut you off there. Sorry, we're getting behind because of technical difficulties, but really awesome work, guys. Really awesome work, guys. Thank you so much.
Thank you, everyone. The ABCD-ReproNim and then the temperament typologies group. I know everyone worked really hard, and sorry for the technical difficulties.
No, it's, you know, GatherTown can be a little bit buggy, it appears. Unfortunately, it didn't happen before today, but that's how it is. All right, thank you. So we're gonna put our next group up now, which is shared and distinct neural correlates of reading and attention. Please come up to the stage.
Hello, everyone.
Hello, Marissa. And we are running a little overtime, so if you could definitely keep it within your time, that would be great.
For sure. I also have to get going soon, so I will make this nice and concise.
Cool, thank you.
So Amaya, Masha, and I spent this week working on our shared and distinct neural correlates of reading and attention. And just some background information for our motivation. Reading disorders such as developmental dyslexia and attention disorders such as ADHD, they happen comorbidly at rates higher than chance would predict. And so the multiple deficit model is one theory that suggests that developmental disorder comorbidity possibly occurs due to a shared risk factor. And this shared risk factor can happen at multiple levels, such as the genetic, the neural, and the behavioral. So if the MDM model is correct, this means that we should be able to see overlap, again, at the neural level that can suggest a potential shared risk factor. So this could be activity that's showing the same pattern in the same brain region for both reading and attention, for example. And so we decided to look for these potential overlaps by using the NIH COG toolbox, the flanker inhibitory control and attention for the attention scores, the NIH COG toolbox oral reading recognition for reading scores, and we were going to look at resting state functional connectivity overlaps. And we were hoping to use a dimensional approach to this rather than categorical. A lot of research that looks at disordered individuals, they will use a categorical approach, but this utilizes very arbitrary cutoff points for who is disordered and who is typically developing. So a dimensional approach will really avoid some analytical issues in that regard. And so our goal for the entire project was, again, to investigate potential functional connectivity patterns that are associated with both reading and attention, so that overlap. But for Project Week, we really focused on reading just because the pipeline we want to use is very new to us. So this was more of like a testing period than an actual implementation. And so the pipeline was using FSL. First, we would use Melodic to eventually do the group independent components analysis. And then in FSL, they have the dual regression, which will break it down into more subject-specific information. And then FSL Nets is a MATLAB toolbox, but can also be used in Octave, which is that open alternative to MATLAB. And this will help us with our connectivity matrix. And so we did have a lot of accomplishments during Project Week, even if they weren't necessarily results. But for the data, we retrieved all of our variables of interest, so the reading and the attention measures from the toolbox, all of our covariates, and we did some exploratory data analysis, pretty much measuring any collinearity issues that might arise. We also managed to get all of our whole brain resting state images and our structural images. And we did this for the entire participant pool, but we did get a subsample separate of 30 participants so that we could test this new FSL pipeline. And so we also managed to start the pipeline, but not necessarily in the way that we hoped. We downloaded all of the FSL stuff and the Octave program locally for testing purposes. And then instead of starting this out in 30 participants, we decided to try 3 for time management. We did start the group ICA analysis, which is still running right now on this computer. So if you hear a fan running, that would be why. We ended up using the multi-session temporal concatenation option, which allows us to start the group ICA right away. But we did want to start with a single subjects ICA first, which would help with cleaning the data. But we ran into some issues with that. So we went right into the group ICA analysis. And so Amaya did an amazing job trying to containerize this pipeline. She got a lot of help on the Slack channel, which was great. She did make a Docker and Singularity image that had FSL Octave and FSL Nets on there, which is great. She got it running on her local machine, but she did not get it to run on Jupyter Hub quite yet. All of our information is also right now on a private GitHub repo. And throughout the course of this, we did try to stick to the data lab commands to make sure we were sticking with all of the proper FAIR principles and everything like that. And so obviously we didn't get any results out yet. We're still in the middle of the analyses, but we do plan on communicating with each other, continuing this project in the future, specifically finishing up this pipeline that is currently running right now with the 3 participants, just to get all of the kinks out, especially trying to get this on Octave because we have not worked with that before. We do plan on attempting the ICA again, but this time starting in the way we originally planned to start with that single subject ICA for cleaning purposes and then moving on to the group ICA. And then we would like to test this pipeline in the containers that Amaya worked very hard on. So I'd like to thank everybody who's helped us out. There was tons of awesome collaboration on the Slack channel. Everybody was so helpful throughout this entire course. So I'd like to thank everybody.
Thank you so much, Marissa. Yeah, I wish that we could all hear everyone clapping because great work on that. And thanks so much. Okay, so we have 2 more groups left. I see some conversation in the Slack. The next one is Neurocorrelates of Pain in Youth, a preliminary investigation to inform future discovery of future biomarkers. And then the one after that is early life adversity. I see Moheb trying to get up to the screen, but okay, there we go. Hey Moheb, if you could turn your video and mic on.
All right, let me share.
Yeah.
Which one? Oh, okay, here you go.
The bottom one. And just quick before you start, it looks like we will be running a little bit over time. I am sorry about that, guys. We'll try and keep it as quick as possible, though. So, Moheb, if you could stay within 10 minutes.
I try.
I'll give you a 2-minute and then a 1-minute warning.
Well, okay, hello, everybody. I had the pleasure to work with Sarah and Ranjita on this project. It all started by meeting during Christina's TA sessions, and we ended up sharing common interest in chronic pain and ABCD. For the first time, we started to collect data on pain in year 2. So we wanted to see whether we can understand functional connectivity and its connection to predicting pain. So one of the main goals is for us to start a seed for future work that looks into predicting pain and trajectories of people who would develop chronic pain in the future as they get older or not. We also wanted to understand whether there are risk factors or resilience factors that we can identify from the ABCD study. So we had goals, and there's rationales behind those goals. One of them is none of us used R and Python professionally, so we are not expert in it, so we wanted to stick with using learning R and Python. We also wanted to do the data management and cleaning using Python. I usually do that in MATLAB. And we wanted also to use data visualization in Python. And as far as the mixed effect modeling, we wanted to basically use mixed effect modeling because we know that we are going to use it in cross-sectional comparisons, and we are going to use it in longitudinal analysis in the future. As far as the machine learning goes, me and Sarah have never done machine learning. Ranjita did some machine learning, and we believe that there are inferences about the brain activity by limited number of variables is not perfect. So meaning if your brain activity is your dependent variables, how many independent variables can you put in there? There is actually unlimited number. So especially with resting state. So in that regard, we wanted to look at machine learning and use whole brain activity to predict behavior. So the first goal we were able to achieve, which is data management and cleaning using Python. So our sample came from the ABCD release 3, because pain was collected only in year 2. We analyzed Gordon resting state function connectivity in year 2 as well. We excluded participants based on the flow that you see here, that highlighted by red in Aguilar et al. And based on the people who answered the question if they ever had pain over the past months or not. So we had about 5,000 people out of 65 possible participants. And after filtering out for missing data, we ended up looking at 4,375 participants. So in data visualization, we just wanted to make sure that we look at univariate variables that we're interested in and understand outliers and their distributions. We also wanted to understand whether the variable of interest differ by category. For example, if if a resting state function connectivity would change if you look at them in male versus female, or in people who said yes or no to pain. I also wanted to look at bivariate relationships. So here, this is an example. We're not really showing results. So the one example to the left is basically a certain function connectivity from the Gordon connectivity, and in the people who said yes or no to pain, but we realized that by doing this, we realized that there's a third category, which is basically the one who refused to answer, which got the value 777, which we needed to basically exclude from our analysis. The one to the right is the same thing, function connectivity, after we filtered out the participants who did not answer the pain questions. So what we learned is that by exploring data, we can understand if there are outliers or not. And we are able to identify the different categories from the visualizing the data. Then we wanted to run mixed effect models on the connectivity. So the rationale behind that is we want to understand the relationship between pain and resting state function connectivity indices known to be associated with pain in adults. So a mixed effect model allowed us to test our main variables while accounting for the influence of other factors. So as you all mostly know that pain comes with comorbidities. So you could be painful, but you also could have cognitive decline, you could have psychological decline. And we wanted to see the effect of these variables on predicting brain activity. By following the code that is offered by Owens et al. That is available online, we're able to achieve our goal of running an R script of mixed effect models. And now we can test our hypotheses and our models using the same script by changing the different dependent variables, which are the Gordon connectivity variables. So this is a non-result of a mixed effect model, one in which basically we looked at the predictors at pain last month, reading, attention, anxiety, depression, and how they affect the resting state function connectivity between the salience network and the frontal network. So no results, and we were not really interested in finding results at that level of research or week. So the mixed effect models allowed us to learn how to allow us for one dependent variable at a time. However, we anticipate that several network and brain region will be associated with that pain. So we can control for those networks in the model, or we can do something else, which is what we're thinking about is to use machine learning. So, so the first goal is to create a machine learning code. So the first rationale is it is hard to understand how certain brain regions are involved in pain that is not experimentally induced. The rationale two, it is hard to isolate or focus on certain brain region in pain research that's based on cross-sectional or cohort-based comparison. Number three is we can use resting state function connectivity connectomes to predict behavior, i.e. pain in a forward inference style. And we are taking into consideration the contribution of the entire brain to pain without making so many assumptions about specific regions. The analysis is finally running and no errors so far. So we might be able really to do some machine learning using the Gordon connectome, functional connectomes. And so what did we learn from machine learning or trying to do machine learning? First of all, we're able to connect the dots using Python, sklearn, and by Dremel. We're able to create the JSON SPIC file that you will include in it the target variable, the source variables or the predictors, the different classifiers. And then we're able to basically, by looking at the classifiers, we'll be able to discuss different things about which classifier works for our solution or not, and also allowed us to understand the different general issues related to machine learning. I would love to thank Satra in particular for his group demonstration and one-on-one late evening and early morning interaction with us. It was wonderful. So with regard to—
Just 1 minute left though, Mohab, okay?
Yes,
thanks.
We use Jupyter Hub. We had a Jupyter Hub repository. We are going to pre-register our analytic plan and hypothesis. We are going to use Data Lab when we create and modify our final data sets. We're going to use a container environment. This is if Gordon tabulated data is not going to be predictive of pain, at least. We might go for other, we might try to analyze the actual fMRI data that minimally processed, which will require fMRI prep and down the line analysis. So we will do that in a containerized environment. And we, of course, use your notebooks, exercises, and other people like Owens research. So we had a little bit of time management, time zone issues, learning new language. Some ABCD variables were had different names, different releases. Some ABCD variables continue to appear in late releases, but they don't have values, and they only have values at baseline. So we got to learn that the hard way. So we are going in the future to register our hypothesis and analysis, get machine learning code to work, and select the problem predictor and classifier.
Thank
I'd
you.
love to thank Christina and Satra and all of you, and I'm done.
Thanks so much. I hate cutting people off. I'm so sorry that I have to.
No,
but thank you so much. Okay,
you.
sorry we're a little bit over time, or will be over time, but we have one more group left and I want to give them their 10 minutes. So welcome up the last group, Early Life Adversity Dimensions, Functional Connectivity, and Change in Child Behavior. Thank you for being our last group.
Thank you for having us and sticking around.
Sorry, Anna.
Oh, no worries. Okay. So this is going to be a presentation that Alexis, myself, and Hajar Nakua will give, as we are all kind of taking the leads on each different piece. Okay, can everyone, I know everyone asks this every time, but can everyone see my slides?
Yep, we can see them.
Okay, take it away, Alexis, when you're ready.
Sure. All right, thanks everyone for sticking around. We'll try to keep this brief. This is a collaboration between myself, Anna, Hajar, Jack, Jenny, and Divya, and we were interested in looking at dimensions of early life adversity, functional connectivity, and change in behavior in ABCD. And so we ended up kind of breaking down our project into 3 questions that all kind of build on each other. And so to start with this first one, we were interested in delineating the factor structure of early life adversity in the ABCD sample at baseline. And so in the literature, there are many different ways to model adversity, but here we considered a really wide range of experiences that are measured in ABCD in an effort to try and identify different dimensions that exist within the data. So in terms of our participant selection, we ended up dropping siblings from the same family, and excluded participants also if they had a high amount of missing data on some of our early life adversity variables. So we ended up with a final sample of just over 6,000. And then we spent a lot of time considering which variables we wanted to include within this factor analysis, because there is a really wide range of data available in ABCD. So we spent lots of time thinking and brainstorming which would be appropriate to include within this factor analysis, and started with a baseline variable pool of 123. And we went through and excluded any that had over 50% of missing data. We also excluded any that had really low incidence within the sample. We also dealt with any multicollinearity. It excluded variables that had really high correlations with each other, and ultimately ended up with a final subset of 58 early life adversity variables. And so first we used a parallel analysis to determine the number of factors that we wanted to retain in the factor analysis. That's represented by the triangles here in this Scree plot. And so the x-axis represents the number of factors tested, and the eigenvalues are here on the y-axis. And so the results from this parallel analysis suggested that we should retain 8 factors. And then if we looked at the bagging enhanced factor analysis, we can see the variance explained by each of these factors. So for example, this first factor, x1, it explains about 10% of the variance. And then if we consider these factors all cumulatively, they explain nearing 50% of the variance. And so here we have the factor loadings for each of those 8 factors, and then the individual variables that are contributing. And so we won't have time to go through these in detail, but we've kind of done a first pass in trying to pull out some themes within each of these factors. And so this first one seemed to be characterized by items that represent experiences of physical threat or caregiver psychopathology. The second one more by poverty or socioeconomic related items, and this R just represents that those items are reverse scored. And the next one, third factor, is volatility in the home environment, so fighting and some like unpredictability. The next, caregiver emotional neglect items, and then one after that was caregiver emotional abuse.
And this sixth factor, when we did the bootstrapping, didn't actually have any items that were stable. So we ultimately will not include these in our follow-up analyses. The seventh factor was represented by caregiver psychopathology, and then the last one by caregiver substance use problems.
Okay, it was interesting to do slide tagging for somebody else. So then we turn to our question looking at the relationship between early life adversity dimensions and whole brain resting state functional connectivity. And Jack, Divya, and I primarily worked on this question, and we really wanted to put the beginning set of a pipeline together to ultimately answer the question of what are the common and unique brain features, brain network features that predict different early life adversity dimensions or factor scores. So we dropped siblings as in the first study. We included only individuals who were recommended based on many different types of exclusion criteria based on their T1, as well as their resting state fMRI. We excluded about 1,000 kids for different types of brain-related comorbidities that would be significant, such as head injury, neurological disorders, or a lifetime diagnosis on the schizophrenia spectrum. We also excluded, when we matched the kids who had imaging data, like past this threshold with the kids who had early life adversity scores, we had to exclude around 2,000 kids, ultimately ending up with a sample of around 3,600, which we then split into a trained test set and also a report set that we're gonna save away till the very end after we make all of our pipeline decisions. That'll be the very last thing that we do. So we've started to come up with a connectome-based predictive modeling pipeline, really part A of our analysis to see, look at accuracy. And then our step B, which I'm not presenting on here today, will be to really characterize the unique and shared features. So we plan to calculate 3 different types of functional correlation, functional connectivity matrices. Z-transforming and vectorizing when relevant. We also plan to use a cross-validation scheme of about 100 splits and run the pipeline that we're going to run for each of these matrices for each of our factor dimensions. And then we plan to test at least 3 different types of regularized linear models. And then obtain initial results from that, model fit scores, the R-squared values, parameter estimates, as well as feature weight, which we plan to then subsequently use for source reconstruction. This is my second 2 plots on functional connectivity matrices, but this was using about 1,500 of individuals in our training set. So this is I just thought really cool to show. We see that, like you can see that there's little brain regions that are correlating together, which is just great. We also we've been getting a lot of help and input this week, and we met with Satra at the end of the day yesterday, and we kind of retooled our pipeline to not start with the most complicated pipeline that I just presented, but to just start with something in a very small subset of our, I said test sample, I just meant training sample, that was wrong. And just about 45 splits just to see if it worked. And so obviously the results here are not really interpretable, they're also terrible. But this is really just one dimension, initially seeing if we could run this initial pipeline and begin to build plots of what things will look like. So we were very proud of that. That was a big goal for us this week. I'll turn to Hajer.
We can't actually hear Hajer. I don't think she's up here on the stage.
Oh, okay. Well, I'm happy to present.
Sorry,
so then it's okay. So in terms of our project goals, we then our ultimate goal is to connect all 3 of these things by looking at what aspects of the experience-sensitive brain network account for the longitudinal association between early life adversity and subsequent changes in internalizing and externalizing behaviors. We just presented looked at some initial baseline stuff and so you'll find on the x-axis here are our different factor scores, as well as our this is internalizing psychopathology. So internalizing psychopathology is on the y-axis, and these are just baseline findings. So we didn't want to like actually go ahead and look at any longitudinal data at this point and peak. We also haven't cleaned any of this DBCL data. So you can see here across the top that both physical threat dimension and caregiver psychopathology dimension was, as expected, associated with increasing internalizing scores, but our caregiver substance use measure was shockingly had a negative association, but that could be, there's a lot of outliers in here.
1 minute.
Below these, yes?
1 minute.
Oh yeah, perfect. This is perfect timing. So below we have what looks like negative associations, but they're actually the same positive associations, because here it's that lower scores indicate higher adversity. So we're seeing some trends at baseline for higher home environment volatility, emotional abuse, and a primary caregiver emotional neglect is being related to elevated internalizing problems, not so much for poverty. And similar trends exhibited for externalizing psychopathology. Future directions, including doing parameter optimization, potentially looking for supraordinate components of our factors, as well as doing some factor validation. We'd like to do dimension reduction, figure out our parameter optimization, and finalize our pipeline for characterizing common and unique network features. And then after all that, we'll be able to do some data cleaning and work on the causal mediation model. We also plan to hopefully get we are using a lot of ReproNim techniques, and we'll continue to do so and really up it, especially in the next month while we have our Jupyter Hub available. And then we hope to submit some of these results to Flux.
Thank you so much, guys. I'm gonna thank you for your acknowledgement slides. I am gonna cut you off because I have one other thing. Thank you. You have done so much work. Your plots are beautiful, by the way.
Thank you. I actually was a little embarrassed of some of the plots. They're not up to my usual standards.
No, I think they're great. Guys, don't go yet, because I made a mistake, and I am so sorry to Matt's team, because I don't know how I skipped over them, but I did. And I think it maybe was because I was trying to deal with like some technical issues in the background. But come on up here, Matt. We have specificity of structural brain biomarkers and psychopathology risk. This is indeed our last talk, I promise. Sorry, Matt.
No problem. Don't worry about it. Let's see if I can get my screen share up. Hopefully that's working.
That is working.
Great. You can just verbally cut in if I start taking too long. I'm not sure I will see any visual cues.
I will. Thanks.
Yeah. So as our study was looking at the specificity of brain volume abnormalities from a parental history of psychopathology, and this shows a foundation for what I'm going to be talking about quickly. A parental history of psychopathology like depression is a well-studied risk factor for development of youth psychopathology. And this has been looked at in the ABCD study. Pagliaccio and colleagues found that a parental history of depression confers risk for depression in the youth. And they also found related subcortical volume abnormalities in the youth, which potentially are a marker for how this risk is conferred. And this paper is kind of representative of a field standard to study the parental-child relationship in sort of within one disorder, as in like parental depression, youth depression, or like parental anxiety and child anxiety. However, this might not be the best approach. This is kind of exemplified by work by McLaughlin and colleagues and with WHO data that found that parental psychopathology is a robust, non-specific predictor associated with offspring disorders, meaning that like any single parental psychopathology might predict a multitude of different youth psychopathologies. So with that said, our main research question is to look at subcortical volume differences associated with parental psychopathology history specific to certain disorder histories, or are they general across disorders? And this is hoping to build on some previous studies to kind of see if risk conferred by parental psychopathology is general in the brain, or if this marker is more specific to certain disorders. And relatedly, we hope to look at if a parental history is comorbid, such as like depression and anxiety, would this risk be greater in the youth, and will this have a greater impact on youth's subcortical volume? We didn't get to it this week, but we also eventually will be looking at youth psychopathology rates related to parental psychopathology history. That's just a question that has already been answered in numerous studies similar to the McLaughlin study I mentioned, but it will definitely be important as we tell our story. As far as our project plan went, our first goal was to create a mixed effect model to examine the effects. The parental histories we looked at were depression, nervousness problems, which we considered anxiety, drug use and or alcohol use problems, which coded as like an addiction variable, and mania. And then we looked at various subcortical ROIs. And our second goal was to look at or try to use the best ABCD-ReproNim practices we've been learning this year. That started with pre-registration, and then I'm also moved to get in data lab for provenance and version control, and finally containerizing. So related to our first goal, I'm not going to go through every single variable. Like I said, we looked at depression, anxiety, addiction, and mania. And we hope to relate those variables to children's subcortical volumes and specific ROIs, as well as total subcortical volume, using various sociodemographic variables as covariates. Regarding reproducibility, as I said, the first step was pre-registration, and I think we found this to be a really useful tool to kind of walk through our analysis step by step before we actually got to it, which means we didn't have to continue rerunning as we found errors because we found them ahead of time. We used a template for secondary data analysis that we found by Weston and colleagues that I found really useful, and hopefully can be a template for further ABCD's pre-registrations. We had help from Arsht for DataLad and GitHub, and that was really helpful. And those should be up. And I believe we're in the process of finishing our containerization to make sure all of our work is fully reproducible. So that was our midweek goal of meeting pre-registration. And as far as our end of week goal of getting some preliminary results, we did manage to get some, mainly last night. The first graph I'm going to show is just some effect sizes, Cohen's D, between various parental histories on the x-axis and subcortical regions on the y-axis. I've highlighted our only significant results. So DA would be depression and addiction, and DAM would be depression, addiction, and mania. And sorry, it was DM, not DA. So the first result was with depression and mania, and the second result was with depression, mania, and addiction. And interestingly, both of these were within the caudate. And another part is I'll have to go back and we have to look at exactly how these variables were coded, but it will be interesting to think about if depression and mania together can be considered as a bipolar history of the parent. That's currently not clear, and we'll have to see exactly how the items were coded. So yeah, both of those are significant results in the bilateral caudate, pretty small effect sizes, smaller than found in the Pagliaccio paper, which was the paper that found depression, subcortical abnormalities in youth, which they found a D of 0.15. And also to know, it was interesting, we found no results specifically for parental depression. So it'll be interesting to see how our study differed from theirs. We'll have to pay more attention to exact methodologies. And I'll get to the idea of ReproNim's replicability because our results do not necessarily replicate theirs. These interaction plots are just specific to the left caudate. Again, we found in the left and right caudate. And they're not going to be very pretty. I didn't have quite enough time to make pretty graphs that also showed error terms. But as far as point estimates go, this is a plot showing the interaction effect between parental depression and parental mania, meaning that the 1 over here is they do meet for depression, 0 meaning they do not, and the blue dot meaning they do meet for mania. So we can see that if a child has a parental history of both depression and a parental history of mania, they had a effect of a higher subcortical caudate volume in the left hemisphere. And it was similar for the right, but that's not shown here. And then for a 3-way interaction, we're looking at this right plot, which means the parent did meet for a history of either alcohol or substance use. Then we have the same interaction between the dots in the 0 and 1 here for depression and mania. So we just saw this effect was even heightened more so when we included an addiction factor in the 3-way interaction. Some limitations to this are we possibly might not have all the sensitivity we need to find individual effects, and actually could be low counts of parental psychopathology histories. The majority of the sample reported no parental history of any psychopathology that was greater than 6,000, which is somewhat surprising, as that would probably not be consistent with lifetime histories of psychopathology as we understand them. So that's definitely a limitation. And then the second limitation is that we considered our analysis based on if a child had any, meaning either mom or dad, history of psychopathology. And this is because there are a number of kids that don't have information from both parents, and we could not get a good way to get around this issue. So some kids are going to be missing information for one parent, and we were not able to look at an additive effect of like one parent versus both parents.
A little bit over 1 minute left.
Sure. So our next step in future plans is we are definitely planning to continue collaboration. This is a really cool collaboration with, opposite sides of the world. So that was a fun opportunity, and we're figuring out how to make the time zones work as best as possible. To answering this overall question we have. The next step will be to focus on interpreting these results and also run similar models to interpret youth psychopathology rates to make sure that story matches up. Yeah, I'll leave it there. And so just again, thank you to the ABCD-ReproNim team. I reiterate everyone else's thoughts. This was a really cool opportunity. I'm glad I was able to participate, learn more about both ABCD, how to do better open science, and meet a fun team that we can continue collaboration with.
Thank you so much, Matt. And I love that you pre-registered. Thanks, everybody. Sorry we went over by so much time, but really thank you, everybody. I see Angie and Dave are coming up here to the podiums because I think they have something to say. This has just been so awesome.
Absolutely, we are just blown away, and here I am on multiple monitors here. Really blown away by all of the exciting things that have happened, not just this week, but since we all started this great journey together back in October. We're really so grateful for the opportunity to lead this, and I apologize, I have children screaming in the other room, so it is definitely Friday afternoon, folks. Thank you for your participation, for your enthusiasm. It was an honor to teach everyone here.
I wanted to give a special shout out that we see Jessica running these sessions, so thank you so much. There's lots of things going on. Extra special shout out to our TAs who did yeoman's work, young people's work. We asked them for many things more than probably they expected, and they did it with a smile, and there was just the best group of TAs. And of course, you students, sometimes this is tricky, but you guys know more about ABCD and more about reproducibility than anyone else, almost anyone else in the world. So yes, it's tricky, but stick with it. You are so well begun to be prepared. And these are tricky things. Take the time, use this to encourage yourself to keep working together, because the village is necessary to make this work. And again, thank you so much for sticking through this this process, and it will continue. Once you're a ABCD-ReproNim attendee, you are always that, and you always have this community to turn to.
Absolutely.
Thank you, Angie, for spearheading all the high-level tips.
Yeah, thanks, everybody. So I know we went over time, but if you can, there's a social hour happening in the game room right now. So hope to see you guys over there. Thanks so much, everybody. I'm gonna call it time. Bye. Thank you.